Hi, welcome back. In this video, we're going to use LHospitals Rule on indeterminate powers. There are three different types of indeterminate powers. We'll do one of each. So the first type is called type 0 to the 0, and it's when you're taking the limit of a function raised to another function. So for example, the limit as x approaches 0 from the right of sine of x raised to the 1 over the natural log of x. So the base is a function of x, sine of x, and as x approaches 0, the sine of x is approaching 0. But also the exponent is a function of x. The exponent is 1 over the natural log of x. And as x is approaching 0 from the right, the natural log of x is approaching negative infinity. Remember, it has that vertical asymptote at x equals 0. So 1 over the natural log of x is approaching 0. So that indeterminate form is of type 0 to the 0. And you can imagine that there is no number 0 to the 0. If the base were not 0, if you take any non-zero number and raise it to the 0, you always get 1, right? But 0 raised to any exponent is always 0. So 0 to the 0 is just undefined. It's not a real number. And so a limit of this type is an indeterminate form. So another indeterminate power is type infinity to the 0. So the base is getting arbitrarily large while the exponent is getting infinitesimally small. So for example, the limit as x approaches infinity of x to the 1 over x. So x is getting arbitrarily large, but 1 over x is getting small. So that's an indeterminate form. And the last indeterminate power is of type 1 to the infinity. Now, the base is a function of x. It's not a constant. It's not always 1. It's some function that's approaching 1, while the exponent is another function that's approaching infinity or getting arbitrarily large, like the limit as x approaches 0 from the right of 4x plus 1 raised to the cotangent of x. So 4x plus 1 is approaching 1, but it's not equal to 1, it's just approaching 1. And then the exponent, cotangent of x, is approaching infinity, because cotangent of x, remember, is 1 over tangent, and tangent of x is approaching 0 as x approaches 0. All right, so in any indeterminate power problem, you have, actually there's two methods. They're very, very similar. I'm going to illustrate both methods, and they're very similar. They both involve exponential functions and logarithms. So we can use properties of logarithms to simplify the powers that we get. You can use either method on any of these indeterminate powers. It just depends on which one feels more natural to you. So I recommend trying both of them out and seeing which one makes most sense. Let's look at the limit as x approaches 0 from the right of sine of x to the 1 over natural log of x. So again, this one is a 0 to the 0. The method we're going to use on this one is rewrite the function raised to another function. We're just going to rewrite it as an exponential. And then we'll use properties of logarithms, and we'll work separately with the exponent and find the limit of the exponent. So I'll show you what I mean. So we're going to rewrite it as e raised to the natural log of sine of x to the 1 over natural log of x. And then we can rewrite that exponent using properties of logarithms. I can bring down that 1 over natural log of x, so I can rewrite that as e to the 1 over natural log of x times the natural log of sine of x. And now if you look at that exponent, that has an indeterminate product form. It's an indeterminate product 0 times infinity, because sine of x is approaching 0, so the natural log of the sine of x is approaching negative infinity, and natural log of x is also approaching negative infinity, so 1 over natural log of x is approaching 0. So we know how to rewrite an indeterminate power as a quotient, so we'll rewrite it. The exponent is really going to be the natural log of sine of x over the natural log of x. And now, let's just deal with that exponent by itself. And then once we find the limit of that exponent, we'll just raise e to whatever we get, and that will be our final answer. So that exponent has indeterminate form infinity over infinity. So the limit as x approaches 0 from the right of just the exponent, natural log of sine of x over natural log of x, by LHospitals rule, is equal to the limit as x approaches 0 from the right of the derivative of natural log of sine of x, which is 1 over sine of x times cosine of x, over the derivative of the natural log of x, which is just 1 over x. Now we can simplify all of that, and we get the limit as x approaches 0 from the right of x over tangent of x. And now we see that we have an indeterminate form 0 over 0. So we can use LHospitals rule again. So LHospitals rule says that this is equal to the limit as x approaches 0 from the right of the derivative of x over the derivative of tangent of x. And now, if we plug in 0, we just get 1 over 1 squared, because the secant of 0 is 1 over the cosine of 0, so it's just 1. And so that limit is 1. And so now the limit that we were looking for originally, the limit as x approaches 0 from the right of sine of x to the 1 over natural log of x, remember that we rewrote that as e to the natural log of sine of x to the 1 over natural log of x. And we found the limit of just that exponent to be 1. So our final answer is e to the 1, or just e. All right, so that method is to rewrite the function you're taking the limit of, rewrite it as an exponential, use properties of logs on the exponent to simplify the exponent, and then just find the limit of the exponent. And at the end, you have to remember to raise e to whatever your answer was. All right, let's do another indeterminate power. So let's look at the limit as x approaches infinity of x to the 1 over x. And remember, we said this one had indeterminate form infinity to the 0. The base is approaching infinity. The exponent is approaching 0. So we're going to use a slightly different method on this one. Instead of just rewriting the whole thing as an exponential, we're going to take the natural log of the whole thing and then find the limit of the natural log. But the same thing happens at the end. Once we get a limit, we have to raise e to that number. All right, so let's start by letting y be equal to x to the 1 over x. Then natural log of y is the natural log of x to the 1 over x. So now let's find the limit as x approaches infinity of the natural log of y. So that's the limit as x approaches infinity of the natural log of x to the 1 over x. And now using properties of logs, that's the limit as x approaches infinity of 1 over x times the natural log of x. And now that has indeterminate form 0 times infinity. And we know what to do when we have an indeterminate product. We rewrite it as a quotient. So we're going to rewrite it as the limit as x approaches infinity of the natural log of x over x. And so now we have infinity over infinity. LHospitals rule applies, and it says that this is equal to the limit as x approaches infinity of the derivative of the natural log of x over the derivative of x. And so now that limit is 0. So going back to the limit we wanted, the limit as x approaches infinity of x to the 1 over x, that's really the limit as x approaches infinity of e to the natural log of x to the 1 over x, and that's the limit as x approaches infinity of e to the natural log of y, and we found that limit to be 0. So this is e to the 0, which is 1. All right, so the methods are very, very similar. It just depends on which one feels more natural to you. All right, let's do the last indeterminate form. So let's look at the limit as x approaches 0 from the right of 4x plus 1 raised to the cotangent of x. So as x approaches 0, the base is approaching 1, but the exponent, the cotangent of x, that's approaching infinity. Remember, the cotangent function has vertical asymptotes. And so this has indeterminate form 1 to the infinity. So we're going to use the first method. We're going to rewrite it as an exponential. So it's e to the natural log of 4x plus 1 to the cotangent of x. And now we use the properties of logarithms to rewrite that exponent as the cotangent of x times the natural log of 4x plus 1. And so now, if we look at that exponent, that has indeterminate form infinity times 0, and we know for an indeterminate product, we just rewrite it as a quotient. And so to take the limit as x approaches 0 of the cotangent of x times the natural log of 4x plus 1, we rewrite it as a quotient. So we're going to write it as the natural log of 4x plus 1 over the tangent of x. So now it has indeterminate form 0 over 0. And now I can apply LHospitals Rule, and that limit is the same as the limit as x approaches 0 from the right of the derivative of natural log of 4x plus 1 over the derivative of tangent of x. And so now I can just plug in 0, and we get 4 over 1 squared, or just 4. And now remember, we're not finished. We found the limit of just the exponent. Now we have to raise e to that number. So the limit we were looking for, the limit as x approaches 0 from the right of 4x plus 1 to the cotangent of x, is going to be the limit as x approaches 0 from the right of e raised to the natural log of 4x plus 1 to the cotangent of x. And we found that limit of that exponent to be 4. So our final answer is e to the 4. All right, so there are 3 different indeterminate powers, and in each one you could either rewrite it as an exponential and then deal with the exponent, taking the limit of the exponent, or you could just take the natural log of the whole thing and then find the limit of the natural log. In both cases, at the end, you have to raise e to whatever number you get for the limit. That's enough of indeterminate powers, and I'll see you in some other video.